Hello everyone, welcome to the 6th lecture on reinforcement learning. Today we're going to be looking at temporal difference learning algorithms. So in this lecture we're going to start by discussing the role of dopamine in the human brain, and we're going to then see how temporal difference learning is actually like an algorithmic form of dopamine, where this reward prediction error theory has become one of the most successful theories in neuroscience. This is going to bring us into a nice position where we can formally define temporal difference learning mathematically, where we'll start by defining it for doing prediction and planning, and then we're going to build up control methods on top of this. Specifically, we're going to build an on-policy control method that learns on the job, and this is like where you're thrown into a welding workshop or something, and some chap hands you a big TIG welder and turns it on, and suddenly you've got to quickly learn about welding bits of metal together. But then we're going to be building an off-policy control method which is able to creatively imagine and explore various situations while actually following a different, more optimal policy. So now if you can imagine watching some expert welder on TV first, maybe you attend some welding classes, read a few books about welding, which teach you how to weld safely, and then when you're finally given a TIG welder for the first time, you've already got lots of experience and you're less likely to burn yourself. So lastly, we'll see how temporal difference algorithms, or TD algorithms, how it relates to Monte Carlo learning that we did last week. And actually there's this full spectrum of methods between the two, which we call TD-lambda. So we'll be looking at TD-lambda at the end. So before we get to the formal definition, I'm just going to start by drawing the similarities to dopamine in the human brain. So specifically, I'll describe the dopaminergic diffuse modularity system, and breaking that term down, it means that we're talking about the part of the brain related to the dopamine neurotransmitter, and this is the midbrain section, and in the diagram the ventral tegmental area, and that diffuses or sends out reward to different parts of the brain. So it sends out signals that spread all over this large area, so it spreads over all of this area to the various components of the brain. And these dopamine reward signals, they largely propagate to the frontal cortical region, so the frontal part of the brain, which, if you remember, we said that relates to our planning and our problem solving ability. So it drives and it determines what our policy is, what our behaviour is, and what actions we take or related to this. For a long time, scientists, we really kind of struggled to understand how this all worked. And in the mid-90s, a team led by Wolfram Schultz, they figured out it was something to do with reward, and it changed the more the animals or the monkeys in their experiments got experienced at the task. But they really couldn't really understand exactly how these behaviours worked and how dopamine was released. And then in the mid-90s, scientists published a paper called A Framework for Mesencephalic Dopamine Systems Based on Predictive Hebbian Learning. And this paper made an important connection between Sutton and Bartow's earlier work on temporal difference methods and dopamine. In particular, they showed that dopamine made predictions about future expectations of reward. So dopamine acted as what's called a reward prediction error, or an RPE, which is the degree to which the value of a reward is unexpected. And this behaves exactly as Wolfram Schultz's early experimental results on monkeys showed. For example, the release of dopamine is based on the monkey's predictors of their reward when they're going to get some food. So if you stop one of these predictors, for example, if there's like a flashing light, the monkey still anticipates the reward based on an earlier predictor, like if it hears a sound. So it learns some distribution over what it's expecting to happen, and the monkey learns to anticipate the reward it's about to experience, and these predictors can be based on multiple different environment stimuli. So since this connection has actually been made, this reward prediction error theory of dopamine has been extensively and independently verified across thousands of different experiments, and it's become one of the most successful theories in neuroscience, with a large amount of quantitative experimental data to back it up. And if I've got two kids, I've got a young daughter, and you can see it visually, they get so excited and they get so much pleasure by what they're expecting to happen. So if they're in the car and they know that they're going to get like a treat from doing well at school, or a present, they're so excited that's like one of the happiest times of their life. Or just before Christmas, they know they're going to get lots of presents, so they can't sleep that night. They're so excited. Then that's like the happiest time of their life is when they're expecting to receive a large reward in the future. So you can strategically develop how your learning works by giving incentives and motivations so that they're expecting to receive something in the future, which motivates them to work hard in the present. So with all that being said, let's actually move on to temporal difference learning, which is essentially just this exciting algorithmic form of dopamine. So to quote Sutton and Bartow, if one had to identify one area as central and novel to reinforcement learning, it would undoubtedly be temporal difference learning, or the TD-learning algorithm. So TD-learning seems to get the best of both Monte Carlo methods and dynamic programming methods. TD methods, like Monte Carlo methods, can learn directly from raw experience without requiring a model of the environmental dynamics, but also like dynamic programming methods, TD learning can update their estimates without requiring the final outcome. So as we'll see later, there's actually like this spectrum of methods between temporal difference learning and Monte Carlo methods and dynamic programming. So yeah, they learn like Monte Carlo methods directly from just exploring around. So they learn from interacting with the environment, but you don't need to iterate through every single state in the environment like you do with dynamic programming. And TD learning is again model free, so we don't need to know how the environment works, we don't need to know the transition probabilities of the structure of the rewards, we don't need to know the rules that govern the environment dynamics, and this really does solve the complete reinforcement learning problem, not just like the planning problem. The main difference from Monte Carlo methods is that we learn from incomplete episodes, and this is very important as it means we don't need to play complete games. We don't need to first play out our entire life before we learn the best policy to make the most money and have the most successful career. Or we don't just need to pass the first exam to figure out the best policy to pass the exam. Instead, we take a partial trajectory and then we estimate how much reward you think you'll get in place of the actual return. And this idea of substituting the remainder of the trajectory with just like this estimate of what we think will happen, we call that bootstrapping, where we update our guess of the value function based on some small local exploration, and then we make another guess. And there's this really nice popular example on this that I think David Silver created, which is that if you're driving a car on a motorway and another car suddenly swerves into you, then you think you're going to die. So you quickly adjust your policy and you swerve away and you survive because you're predicting that you're going to die. But with temporal difference learning, you learn from that scary, nasty experience, and you learn to swerve away, and you learn that that was the right thing to do. However, in the case of Monte Carlo methods, you only learn from a complete episode, and in this case you would learn something in the event that you've died when your life is over. And if you happen to survive, then you wouldn't learn anything from that experience, which, to be honest, isn't really that great. Okay, so let's now recap the Monte Carlo algorithm, specifically where we estimated the mean return as a running mean. And if you remember, we incrementally updated our mean estimate a little bit by that alpha value here, towards the error of the value function, towards this error, the bit inside the brackets here. And do you remember how we hinted at not needing to care about the value of complete episodes here? So we don't really care about the past so much. Remember we said we could get rid of this 1 over nst and just replace it with this sort of little bit parameter, this small change like the learning rate effectively. And the new observations are basically much more important to this process. So, well, you can see we're in this kind of setup now where we're looking at algorithms that just move a little bit towards the observations we've seen. And every time they observe the value from a state, they update their estimates accordingly. And this allows us to formally introduce the temporal difference methods, which now break up the episodes and use this idea of incomplete returns. So with temporal difference learning, the goal is the same as before. We're trying to learn our value function, this v pi, so that we can evaluate a given policy. E.g., just for prediction, we'll talk about control in a little bit. So we're trying to work out the value of how good it is to be in a particular state. So the agent just wanders around with some policy, so for example a random policy, and we want to know how much value we can extract from being in that state on expectation. And we're trying to do this online, which means that every step we're going to do, we're going to try and learn something in every step to update our estimate of the value function without waiting until the episode finishes. And just like before, we want to update our value function a little bit in the direction of some error function. So just reading this first equation here, we say we're in some state, st, and we want to update our estimate of this state. We want to update our value function a little bit in the direction of this estimate of the value function, and our estimate in this case, Monte Carlo methods, was the full return. And then if you remember the Bellman expectation equations, we were able to sort of break this return up into a more local condition. So now we're going to use the simplest version of temporal difference learning called TD0, and we'll discuss what that zero part of the definition means a bit later. But what this means is we're going to update our value function just like before, and we're going to use the way dopamine works towards some estimated return after just one step or just a little bit into the future. We're going to say how much reward are we expecting to get at this point. And the estimate has two parts, like in the Bellman equation. We have this RT plus 1, which, if you remember, was the immediate reward. Oops, sorry. We had this RT plus 1, which was the immediate reward. And then we added the discounted value of being in the next state. And that's identical to the Bellman expectation equation we defined all the way back in lecture 2. So do you remember we had those series of identities which were defined from the return? You can see this is equivalent to just Monte Carlo, but we don't need to compute the entire episode. We can just substitute this in to get our nice temporal difference learning algorithm. So it's all kind of formal and well defined. And this, we call this red term here the TD target, whereas the whole bit inside the brackets here, we could just call it the TD error. And that error is the difference between the estimate before and the estimate after taking a step. So this example here is straight from Sutton and Bartow's book, and it helps kind of demonstrate the differences between Monte Carlo learning and TD learning. But the basic idea is that you're driving on your way home from work and you're trying to estimate how long the journey is going to be. And with Monte Carlo learning, you have to wait until you get home. And when you've got home, you calculate your total travel time or the return, and then you go back to each of the states before and you updated how long you thought it was going to be from that state towards the end. So it's like you go home and then you work it, then you know your final time, then you say, when I was in this state, this is what my estimate was going to be. When I was in this state, this is what my estimate was going to be. So you correct the error from those complete episodes. However, with temporal difference learning, you update your estimate immediately as you're driving along. So immediately as you're leaving your office, you may see that it's raining, and therefore you expect longer queues, and so you're going to say your estimate is sort of up here somewhere, longer than it would be on average. Maybe on average it's down here somewhere. But then when you actually get into your car, you see there's no traffic. The usual traffic jam outside the science site is gone, or wherever you're expecting there to be a traffic jam. So you then say, oh, maybe I'll get there a bit shorter than usual. So you update your estimate again based on that little bit of experience. And then you exit the highway, you may join into some really long queue, and then you're like, okay, actually it's going to take ages, so update your estimate again. And then maybe you finally get off and you're stuck now in gridlock, so you have to update your estimate again, yet again. So you've sort of corrected all your estimates as you go along using the experiences you're receiving. So you see with TD learning, you can directly learn from the experiences as you go. So it's called on-policy learning. So I'm just going to have a look at some code to do this, and you can see the links to this code on Duo, the Qlearning link. And like you'll see from before, this is the Frozen Lake OpenAI gym environment, and we've disabled the slippery environmental dynamics just so that we can see the solutions a little bit more intuitively. then I've got the same setup helper code here where we can just plot the policies that are learned. And this is TD0 prediction. So again, there's no control in this so far. This doesn't involve the problem of learning an optimal policy. It's just trying to estimate the value function using the TD0 algorithm. All it does is it iteratively applies the Bellman expectation equations, and I'll show you how this works. So we start out with a value function which is initialized with zeros everywhere, and then we don't need to go through every state this time, like we saw in previous lectures and like we saw in dynamic programming. But also as in Monte Carlo learning, we don't need to go through an entire episode before we learn. We can just learn on the job. So let's have a look at that. We just start playing an episode. We start at some state, and then we just start iterating. And what we do is we start with some random policy. So we're just evaluating the value function for this random drunk agent, which is wandering around and stumbling around. And it samples this random action here with equal probability of taking any action. It gets this next state, the reward from the environment. And then here's where we just implement the TD0 algorithm. So we move the value function a little bit in the direction of the TD target, which gives the full TD error term, where the TD target is the immediate reward plus the discounted value of the next state minus the current value function. And that's all it is, very simple, and you iteratively apply that. And this gives you an estimate of the value function for that policy, which in our case is the random policy. So it doesn't solve the control problem, but it does tell us the value, so we can actually use that to do a single step where we update our policy here, and we plot it, and this is the results we get. So as you can see, it started to learn a reasonably good policy. It's obviously not perfect, but you can see it is actually this process of it does actually learn the value function for that policy, and in one step it can start to improve the policy from a random policy rather than just randomly going everywhere. So it's not too bad after one greedy policy step, but it's not perfect. We really need to do control, so we need to add some functionality here which allows us to optimize the policy as well. Okay. So how are we going to add control? Well, like we did in the last lecture, we're going to extend our prediction approach by adding control, which follows a very similar idea to what we did in the last lecture, learning an optimal policy for the Monte Carlo methods. So the most obvious algorithm for doing this is called SARSA, where we're just learning on policy. So the agent starts in some state action pair. So if you remember, we do this with the Q values, with the action values. So we start in some state action pair, and we're going to just update the Q values here. But basically we're going to observe some reward from the environment, and then this reward is going to take us to some new state, and then we're going to sample our own policy in this new state to generate a new action, and then putting that all together, we're just going to go state action reward, then the next state, the next action, the next reward, which is going to be why it's called SARSA. So this gives us this update pattern at the top here, which is very similar to how we did it with the value, just as you saw before, to do prediction, but we're just going to do it with our Q values. So we start with our Q values here, and we move each Q value a little bit in the direction of our TD target, this part in the red, and this is just the reward plus our discounted Q value of the next state, minus the Q value of where we started with. So just to repeat all of that with an example, it's like you're in some state and you're maybe considering some action. So maybe if you remember that example where we're in the beautiful Bright Angel Trail in Arizona, but maybe you have some really stupid policy, maybe you've had too much to drink or you've been taking drugs, so you're considering jumping off the cliff. So what we want to know is whether this is a good policy. So if I actually take that action and look at the reward I got falling off the cliff and breaking my legs, then if I look at that value of the next action that I'm going to take, and in this case it would be stuck with a broken legs, maybe I'd be dead and unable to keep walking and get that beautiful view. This one step look ahead gives me an estimate of the value of that stupid policy, and I can use that estimate to update the original value of that state action pair. And hence I would realise that was a stupid thing to do, and it's a bad policy to take drugs and have too much to drink before going hiking. Or similarly with the example of the two cars swerving into each other, you can predict that you're going to scrape the car or even worse crash, so you know that you should be swerving away. And like in the last lecture, if we combine this strategy, if you combine it with the greedy at the limit of infinite exploration, or that Qli idea we had, where we start off by doing lots of exploration and then we slowly start to exploit the environment, this does actually converge in the same way of learning the optimal policy. So remember, if we're storing all of those Q values globally in that large table at the top here, these can be cached and they can be reused later on. So for example, if I end up in that state again, where I'm considering that action again on that trail, or I'm in a similar state, maybe the action has like repetitive cycles in it. Sorry, maybe the environment has these cycles in it, like if you're on a racetrack in a car and you're considering making a turn which would cause you to crash, then you're going to learn from that experience because it's cached and reused in this global table here. So like if you're on that trail and you're considering jumping off, maybe later you read like a cult book which tells you to jump off cliffs for whatever reason, you're going to have already used that experience where you previously thought about the predictions of those future awards, and you're going to reuse that stored knowledge where you did that processing last time, and you're going to say, no, this is a really bad idea. And this will help us to learn much better policies in the future, like not taking drugs, not reading cult books, or drinking too much before going hiking, and so on. So instead, maybe this is going to like encourage you to eat chocolate, read educational books, go on hikes effectively, prepare your gear, and eat healthy, hearty meals before going on a walk. So SARSA really is an on-policy learning algorithm, and we're selecting actions and evaluating that policy. We're learning on the job. But remember, right back at the start when we talked about learning, having a process of reflection. Do you remember back in the previous lecture right when we defined learning, even at the beginning of deep learning, we talked about there being this reflective part of learning. We can actually learn off policy. So we can imagine this behaviour of jumping off a cliff and breaking our legs. We don't actually need to do it to learn from it. We can imagine that being a bad thing without actually doing it. So let's explore this. So far we've been learning on policy learning, where the policy we've been following is also the one we're learning about. But have you ever had a good idea in the shower or while lying down in bed with the lights turned off? Well, actually, when we're in a relaxed state, doing light exercise, so taking a shower or lying down in bed, what actually happens is we get an increase in the dopamine flow in our brain. This relaxed state triggers an additional release of dopamine. And therefore, we can actually predict how things are going to work out a lot better. With increased dopamine in our frontal lobe, we can actually form new connections faster. We can make more connections. We can connect prior knowledge better. We can plan better. So instead of just coding an idea for your coursework, waiting hours for it to train and fixing bugs and using countless collaborative resources, maybe just like take a shower, then lie down in bed when you're feeling really clean and having clean bed sheets. And then what you might find is that, because you're kind of tricking your brain, you might be able to imagine how that idea is going to work without even doing it. And as a more kind of experienced researcher, I find myself needing to code less and less and less. Don't need to sort of spend so much time bug fixing. You can instead like imagine how your ideas are going to work and how they're going to end up when you've got more prior experiences you can build on. So we turn our attention to relevant past experiences, and we reuse those insights that when we know, oh, that's not going to work because I tried it before, and we can make these much more deep and insightful connections as we get more experienced. So in other words, as humans, we do learn off policy. We learn by observing others, and we think to ourselves, maybe I could do better if I followed that example. As I'm speaking right now, my mind is also thinking, maybe I could have explained the past algorithm a bit clearer. Maybe I could have used more metaphors in the next slide. Maybe I need to hurry up or slow down if time's running out. So later tonight, after having a shower, I may go back and reflect on how this all went, and I may re-examine all the things that went well and all the things I can improve. But the most convincing reason to go off policy is that I think by definition, the Bellman equations, we can see that the optimal policy gives us no room for exploration. So there's no creativity if you behave optimally. If Mo Farah wants to win his race, he has no time to start learning to play the piano each morning. So we really need to explore the state space effectively at the same time as behaving optimally. So therefore, we have to do some we have to have some arbitrary exploration policy. Let's call it pi of A conditional on S, which explores around as much as it likes. It's a very creative person, always thinking of new ideas, but at the same time, we need to learn about the optimal policy, like that athlete with their rigid early morning exercise routines. So now there is a method you'll encounter in Sutton and Bartow and other articles online called off-policy Monte Carlo learning with importance sampling, but I won't be covering that in detail because it has extremely high variance, which basically means over many episodes your target policy and your behaviour policy, they'll never get close enough to being useful. So therefore in practice this method is effectively useless, so I'll spare you the mathematical derivations for that. So you have to use TD-learning when working off policy. There's this importance sampling equivalent version of TD-learning which increases the variance of TD-learning, so it can still have instability issues, but it's much lower variance than Monte Carlo. But basically you multiply your TD target by the ratio of the optimal policy you're evaluating to your current policy that you're following, so it's pi over mu. Maybe I'll just really quickly show this in the notes. So basically we're just going to move the value function being in some state, so we're going to update it a little bit by alpha according to some ratio. So we're going to basically weight, in fact I might just write this part out. So we're going to have the same thing as before. We're going to have the reward at the next time set, or the immediate reward plus the discounted, sorry that's meant to be gamma, value of the next state, st plus 1. Okay, then we're going to minus the current value function, so that's what we've just seen. But with importance sampling, we're going to weight this by the ratio of the exploratory policy to the current policy. So we're going to have this we'll just say the policy we're exploring, so this creative artistic policy if you like, imagining all of the ideas, is pi of the current action conditional on some state according to this policy, this exploration policy, to the current policy that we're on, which can be represented as mu of the current action conditional on being in some state. So we weight this update based on this ratio here. This is the importance sampling strategy, which increases the variance. But if the two policies differ too much, if there's too much difference here, this will diverge off and nothing here is going to get counted. So it's quite a nice idea. So the idea which works best with off-policy learning is known as Qlearning, which is specific to TD0. If you look at the equation at the top here, you'll see this is just again the Bellman equation again, but this time you may notice there's actually two policies in there. We take actions AT, which is just our exploration policy. In this case we're just using an epsilon greedy policy, but now we also have the optimal policy which we've substituted into the second part of the Bellman look ahead, which is the optimal greedy, or this max Q policy, which doesn't allow for any exploration. So we're taking our Q values, we're updating them a little bit in the direction of the immediate reward plus this max Q, minus our so this is like this other policy from our Bellman, the optimal greedy max Q minus the current Q values here. So we've got this policy here and this policy, or the immediate reward here. So what does this mean? Well, again, reading the equation here slowly from left to right, we're updating our Q values a little bit by this alpha in the direction of some TD error, which we're defining to be the reward here that we observe, plus the discounted value of the next state when following some greedy or alternative optimal behaviour, and that's the TD target. And then we minus the behaviour of following our original policy, giving us this whole TD error. And that's a valid interpretation of the Bellman equation, but it combines the optimal policy while also following some exploratory policy, and this allows both the policies to improve. And we can actually just substitute this max Q part here with any other policy we like, which gives us a more general case of policy Qlearning, and we might come back to that a bit later on in the course, but where you simultaneously optimize any two different policies. But this special case here, where we greedily choose the optimal Q value, is particularly elegant because it allows us to simultaneously find the optimal policy while exploring the environment via some exploratory or creative policy. And this special case we've shown here is well known as the Qlearning algorithm. And the algorithm here basically just shows a pseudocode implementation or like a NumPy implementation of Qlearning. And you'll see it's just one of the shortest and simplest algorithms so far. So it's very, very efficient and acts and very powerful base to build on. Qlearning also converges on the optimal action value function. So we start out with some action value function. We go through our episodes. We have some random epsilon greedy policy by epsilon on some hyperparameter. We could use greedy at the limit of epsilon if you wanted. Greedy at the limit of infinite exploration, I meant. But this is just a simple random epsilon greedy. We sample our actions from this random epsilon greedy policy, and then we just update our Q values as according to the equation by some little amount times the reward plus the discounted value of our greedy policy minus the current policy. We update accordingly. So I think that's also shown in the code. This just shows the SARSA implementation that we talked about, where we just had our random epsilon greedy policy. This was just the previous SARSA, and this was the SARSA objective we updated, which was on policy. And this plots the results for that SARSA. So yeah, okay. And you can see like these plots here just show like at the beginning the epsilon length is quite short because it hasn't yet found a place with lots of reward, and it maybe just falls into some holes or something, and then eventually it finds longer episodes over time which get more reward, and the reward starts off with no reward as it's just falling into the immediate ice. And then later it discovers randomly a policy which it can start to use to exploit the value from, where it gets more reward. And then it does learn the optimal policy, which is SARSA. And then this is just showing what we've just seen, the off-policy Qlearning approach, that really simple algorithm. So we start with our Q values initialized and cached in global memory. There's a big Q table. And then we go through some fixed number of episodes, where we sample from our random epsilon greedy policy. We choose an action from this policy, and then we update our Q values by alpha a little bit in the direction of the immediate reward plus the discounted value of our greedy policy minus the current policy. So that's what we've just seen. And this also, if we plot it, converges quite nicely. So it starts out not discovering anything, and eventually it finds the reward and it starts to exploit it, and we get this nice GC value function. And it's learnt the optimal policy as well. So just to recap what we've done so far, we've currently defined the temporal difference learning algorithm by replacing our estimate of the return by a local form from the Bellman expectation equation. And then we built a couple of control methods on top of this. We had the SARSA method for on-policy control, and now we've just defined Qlearning for off-policy control. And in the past I've mentioned there's actually like this whole spectrum of methods between TD-learning and Qlearning, which is what I'll show in this last slide here. So what you can do is you cannot compute the full return when we can create our TD target. So for example, you could just let the TD target look n steps into the future, and you could also adjust that n to be somewhere between Monte Carlo and TD0. So in practice, doing that is a bit of a pain to tune, as tuning n strongly depends on how long the agent walks within the environment, so it doesn't really generalize well across different environments. But there's actually a much more elegant solution, and that's to do a geometric averaging of these n-step updates in such a way that defines this spectrum between Monte Carlo methods and TD0. And the amount we weight between those is controllable by what's called the trace decay parameter, or lambda. And lambda is just in some interval 0 to 1. And the first part of the first part of lambda minus 1 here, it's just like some normalizing factor effectively that ensures that all the weights sum to 1. But setting lambda to 0 reduces the equation to its first component only, which is equivalent to just a one-step TD update, as in TD0. But whereas setting lambda to 1 reduces the overall update to its last component, which is equivalent to a full Monte Carlo update. So we can actually tune lambda now to basically interpolate between the TD0 and to a full Monte Carlo update. And the full derivation and analysis of this is a little bit too much for like a 1-hour lecture. But if you want, you can read chapter 12 of Sutton and Bartow's book if you want to get more clarity on that. But in particular, it turns out to be just as computationally efficient to implement this geometric weighted decay, and it's actually the same cost as TD0. So by following this implementation, we've got a way to control this spectrum of methods between TD0 and Monte Carlo. And if you're asking the question like which one is best, basically this is again a bias variance trade-off problem, and it depends on the application, depends on the sparsity of rewards, the number of states, the distribution of those actions, and so on. So if you look at the diagram here, particularly at the top, you'll notice with TD0 or SARSA 0, learning by a one-step SARSA, you'll see that all the points along the path here don't give you any reward. You need to wait until you reach the very last state here, and then the next iteration it will back up and you'll be able to find results here, and then the next iteration you'll back up and find a value here. Therefore, you need hundreds and hundreds of episodes for the results to backwards all along this path here before you get the value function of them. You need lots and lots of episodes and games to do that before you can propagate backwards. So you're only propagating the information backwards one step at a time with SARSA 0. But with TD-lambda here, you actually increase all the state action pairs along the trail according to your eligibility trace and that trace decay parameter. So all of them get updated a little bit in the direction of what's actually happened, propagating all this information backwards through time. So this lambda should be treated as like a hyperparameter, and it should be tuned accordingly. There's usually some sweet spot for lambda around 0.95, but it's not always the case. So yeah, in summary, this lecture has introduced TD-learning, which is a model-free approach, and we've seen that this behaves just like dopamine does in the brain, where we're expecting reward in the future, we get excited by the reward we're about to receive, or we're expecting what the value will be in the future, so we can adjust all of our weights, all of our parameters, all of our dendrites according to what we're expecting to happen, so we can learn from actual experiences rather than having to play through our entire life and then backtrack through our entire life's experience to find the value of every state we've possibly been in, which is very inefficient. So TD-learning is very computationally efficient. It's probably the main algorithm we tend to use, these kind of strategies in reinforcement learning or variants of it. And Qlearning does actually converge to the optimal action value function, so it allows us to find the optimal policy, and it's all derived very nicely from the Bellman expectation equations. Then we saw how there's this spectrum of approaches between temporal difference learning and Monte Carlo learning. So up to this point, you're probably still thinking about your coursework a lot, and you're probably thinking, well, how does this help me with my coursework? You've already shown us a Qlearning algorithm in the sample code, and it's even doing crazy things with deep neural networks. Well, hopefully the next lecture will be the one where this really starts to make sense and clarify and sort of tie everything together, where basically what we're going to do is we're going to, rather than use tables for our Q value function, we're going to start using deep neural networks or function approximators, general functions, to approximate our value functions. So we're now going to basically scale these methods up significantly. But up to this point in now, we've really laid down all the groundwork. We've now got all the foundations of how these things fit together, how they come from the Bellman expectation equations, from the Bellman optimality equations, how we can use them to solve general purpose MDPs. And now we've got these tools. We've got this view of going from dynamic programming to Monte Carlo programming, where we don't need to iterate through all of the states, to now iterating through trajectories. And now we've even broken that down further to TD methods, where we're just learning from the immediate reward and the discounted value of the next state. So next we're going to be approximating these action value functions, these gigantic tables we're currently storing which aren't scalable. And then we're going to build on some of the properties of doing that. It's not a direct, obvious extension to these tables. We can't just straight away throw a deep neural network on, because we'll see there's issues with convergence which crop in, which need to be addressed. And we're really going to start to introduce function approximators for the remainder of this course. But yeah, I hope you've now got quite a solid foundation and feeling for how this all fits together. Do read some more of Sutton and Bartow's book if you're unfamiliar with any of this, because that's an excellent resource. But yeah, that's everything. So I hope you have a good week.